All right, so I've decided to remake my mega sliding tutorial, that 1 hour long, I think it's even over 1 hour long sliding tutorial that I made some time back. Yeah, so there were, for one, I will say that the code, how I wrote the code back then, um, the code has evolved over time. I've added new features. I've, redesigned the code, structured it in a better way. I've just grown a lot as a developer over time. And so I think this warrants a remake. And yeah, this time I'll actually publicly share the place file so that you guys can, easily copy and paste, this script. So I'll make it freely available. And this video will just be me literally scrolling through the sliding script and then giving an explanation for the reasoning behind different parts of the code. So this is more so just an explanation video. All right, let's get right into it. So in our starter pack, we have the slide hitboxes, and these are the hitboxes that are going to go onto the player's feet. And these hitboxes will allow us to detect the ground when the player is sliding. And so I've just copied and pasted that hitbox model into Workspace. And yeah, so you can see there's one for the left foot and then there's one for the right foot. And they are accessories. And the reason why I made them accessories is because it makes it really easy to weld these boxes to the character's feet. And why is that? Well, the cool thing about accessories is that you just have to put an attachment inside of the handle part and give a particular name. So this attachment is deliberately named left foot attachment because when Roblox sees that, it knows to take that hitbox and then put it on the player's left foot. Because the thing is that if I were to uncollapse the player model, and then if you were to look at the character's leg part, it actually has an attachment under it. Like if I run the game, that says left foot attachment. So that's how it knows like how to match these accessories with the parts of the player. So yes, so you can also see that this left foot attachment has a position offset on it, because the reason why we have this -1 offset is because normally if we said 000, then yeah, I can actually let me edit the one in Star Pack since this one being used. If I just put 000, you will see that it will center these hitboxes right at the player's feet, and we don't want that. So now you see how it centers it right on the player's feet. And then just to show you what I was talking about in regard to the player model and these attachments, if you look at these legs, they also have an attachment as well. So that's how you know where exactly these hitboxes with the corresponding attachments will be attached. And so that's why I added an offset there to be -1. So that, let me see, -1 as well. If I play the game, now you see that it's up the character's leg. All right, so that is the hitbox setup, and yes, we have it in starter pack. Right, and so now you might also wonder what these damage or DMG point attachments are inside of these hitboxes. And these are for the Raycast hitbox module. This is the module we will be using to cast rays to the ground to do hit detection. So these attachments determine the origin point of the rays. So pretty much this is where the rays are emitted, the point from where the rays are emitted. And this is the part of the this face of the box is the part that is going to be in contact with the ground. So that's why those attachments are on that side. And the reason why they're named DMG point is because the hitbox module specifically looks for attachments with that name. So basically, I'm going to go ahead and give you a quick preview here. Before Raycast module. Yeah, so when you create an instance of the Raycast module, this is a quick preview, so you don't have to really understand right now, but I'm just going, for the purposes of some context, I'm going to cover it here. So when you create a new instance of the Raycast module, you pass it an object. And then what the Raycast module does is it looks through all the descents of that object and tries to find these attachments with the name DMG point. And it pretty much just compiles like all those attachments together. And then that is basically what makes up a hitbox. It's just a bunch of like points, and you know, rays are emitted from those points. So before I start covering the sliding script, I think it's important to talk about the Raycast hitbox module because it is central to how we will be able to detect hits against the ground. And I've made some modifications to this module. But before I talk about the modifications I made, I want to talk about how it currently works and why that necessitates some modifications for our purposes. So here I'm going to explain how the current Raycast hitbox module works. So let's take the example where you're creating a combat game and then you're trying to create trying to do hit detection for punches, right? So you have a character, you have, you know, the character's fist, and then, you know, you have a punching animation. So the character's fist is moving, you know, frame by frame. And let's say that maybe, and this is the character's fist in one frame. This is like the front of his fist. And then the next frame, the character's fist is like this. This is a very bad drawing of the character's fist. But if you go on to use Raycast hitbox for hit detection, what you might do is you might, you know, add attachments to the corners of the character's fist. And by default, what Raycast hitbox module does, you might wonder, okay, how does Raycast hitbox module? Okay, so cool. These attachments, these are the origin points for the ray, right? But then how does it know what direction to cast the ray in? And so the way it knows that is based on the previous position of the attachments, right? So what it does is that it calculates a vector, and it's a very simple vector. And this vector is simply the distance between the current position of the attachment and the previous position, right? And it just takes that vector and then projects it forward as the new raycast. And so the cool thing about this is that the length of this vector depends on the speed of the animation, right? So if you have an animation where the character's fist can drastically change from one frame to the next, then that means that the rays that it will cast in the next frame will be longer. But if it's shorter, like, maybe the character's fist didn't move much, like maybe this was right here, then, the rays would be like, shorter. And yes, so it's really cool that it works this way, because that means that your hit detection will be accurate within the frame. And this is also why it's important to make those animations in such a way that you have good like in between frames. Otherwise, when you end up in a situation where you're casting these longer rays, it could be that these origin points already within the whatever enemy you're trying to hit. And the way raycasts work is that for the raycast to be able to detect that you hit something, the rays have to originate from outside that thing and then enter into that thing. Like if you were to say that this is a part, it has to enter into that thing. If the ray started from within and then went out, then it won't detect this part. So that's the importance of having shorter rays, is because they give you your hit detection higher resolution, basically. But anyways, enough about that. I just want to highlight how it currently works. So for the purpose of sliding, we don't want this behavior, right? Because if you imagine the fist to be instead of the character's leg, then all it will do is from frame to frame, it would just, cast like a straight line, because the character's leg it's just moving in a straight line. So this is not what we want, but rather we want to basically cast the same ray relative to the C frame of the character's leg. We want to cast the same ray, just going downwards every time, right? And so we have to modify it so that we'll be able to pass in a vector, a direction, which will be relative to the C frame of the character's leg, that this raycast module will cast every frame. So as discussed in that demonstration, we want to be able to pass a fixed ray direction, which will be relative to the coordinate space or C frame of the character's leg, and it will cast this ray every frame. And so that is the first modification, is the addition of this ray direction. And then also I've added this on hit nothing event, because we're going to be interested in knowing when the characters, those hitboxes, if the character is not touching the ground, we will be interested in knowing when that happens so that we can properly exit the sliding. So I've made some modifications to the hitbox caster module, and so as I said, I've added this on hit nothing event, so that means that when we destroy the hitbox, we need to clean that up as well. And if I scroll down further, so I also added the ray direction parameter, and so here's where we're actually using it. And so here a point is just one of those damage point attachments, the DMG point attachments. And so so they have a, because instance one, this is just the attachment instance, right? And then that has a world position property and like a world C frame property. So we're just saying that the origin point from where we want to cast the ray is simply the position of the attachment. And then the direction that we want to cast the ray in is the ray direction, but relative to the orientation of the attachment. But the orientation of the attachment is simply just the orientation of the character's leg, right? Because the attachment is a child of the hitbox. But the hitbox is, when it gets attached to the character's leg, is just a child of the character's leg. So ultimately, the ray will be casted relative to the character's leg. And so that's what we do here. And then this is where the ray actually gets casted. And then also the Raycast hitbox module has this ability to visualize the rays for debugging purposes. And so we need to make modifications to that, so that, because we add this ray direction, parameter, and we need to modify this so that it also visualizes that correctly as well when we're using that parameter. And so we're saying that, okay, if we're using that ray direction parameter, then this is basically the C frame that you want to use to visualize the ray. I just took inspiration from this, because if you look at cast mode visualize, and cast mode visualize is nothing but, if you go to visualize cast module, this might be the wrong one. Let's see. Yeah, this is the right one. So this visualize, all it's simply doing is that it creates a C-frame lookat where the position of the C-frame is just the position of the attachment, and then you're going to look at, a point, and the point that's looking at, by default, right, when you're not using ray direction, as I discussed in that demonstration, is that it creates a direction based on the previous position of the attachment, right? So that's why it's like this, but I'm just taking inspiration off of that and then doing the same for our scenario, where we just want the direction to be looked at to be the origin point, which is the attachment's position, plus the direction that we passed in. And so we just want to look at that point. You get what I mean? And yes, and then so the very last modification I made was this. I added this Boolean, did ray hit something? And basically this for loop loops through all the attachments that are part of our hitbox, right? And if we indeed, if we hit something, then Raycast result will exist. And then we'll say did ray hit something equals true. So if any of one of our rays, landed, then we hit ground, so to speak. So in that case, if we didn't hit ground, right, if none of our rays hit, then I know we didn't hit ground, and so I fired that on hit nothing event. So yeah, that is all as far as modifications to this Raycast hitbox module. So the first thing we have in the sliding scripts are just some references to services we will need. Not much going on here. References to instances like the character, human or root part. And here we are, here we're establishing the ray direction. Remember, this is relative to the character's leg. And so this right here is that ray direction. And this detect the ground ray direction, this is for the initial detection of the ground, because obviously when the character is not in slide mode, he's just walking about, and then he decides to enter into slide mode, we have to see that there is ground for him to slide on in the first place. So all we do in that situation is that we cast a ray directly down, like below him, to see if there is ground. And when there is, then it puts him into slide mode, And in slide mode, it will use this vector to continuously detect if he's, still sliding on ground. And these are some Raycast parameters. Pretty much we're saying that we don't want the rays to detect hits against any descendants of the character. So pretty much any child of the character, we don't want to detect hits against that, including the hitboxes. And we exclude no water. Unless you want them to slide on water, then you can set it to false and then, make this work on water. Sliding attachment. Oh yeah, this is for align orientation. So align orientation is what will allow us to orient the character, like, the rotation of the character to be parallel to the surface he's sliding along. And we set rigidity enabled to true. This is important because we want to be able to change the orientation on a per frame basis, right? We don't want to have it take multiple frames to reach some goal orientation, right? We just want to be able to adjust frame by frame to the slope of whatever environment he's sliding on at any one frame in time. And yes, we parent this to the humanoid report. And then we also parent the sliding attachment to the humanoid report. I forgot what this is. Oh, okay, I guess it's just for align orientation that we create the sliding attachment, right? Then these are some constants that we'll be using in the script. So the slide acceleration is simply when you press the key to slide, just how much acceleration you get and how much initial acceleration you get in the direction you're moving. And so, this is independent of the character's mass. It doesn't matter how big what the character's mass is, it'll always apply this acceleration. Then there's this. Oh yeah, this is not relevant for this tutorial. So I'll remove that. At least I don't think so. Yeah, we don't use it. Cool. But that was there for, like, if you want to add the ability to, control the direction of the character while he's sliding. But that's not part of this tutorial. And then I've added this airtime before slide stop. So basically what this is when the character is sliding, and let's say that, we don't detect ground, right? This is like the amount of time that, because normally if we don't detect ground, we'll, you might say, okay, just take him out of slide, right? But we don't want to do that because let's say that he's sliding over particularly bumpy terrain, then it'll be a little bit abrupt if he just, exits sliding. So we're saying here is if he's been in the air for longer than 0.2 seconds, or he hasn't touched ground for 0.2 seconds, then take him out of sliding. So you can actually see this in action. So when I slide, you can see, here, as soon as I get off this platform, I'm now on the ground, but it doesn't take me out of sliding. I'm able to continue my slide, and that creates for, visual, continuity. And, even here when I slide off, you can see that obviously, when I'm falling like that, I would not have touched ground for 0.2 seconds, and then it transitions me from sliding to falling. So that's just a nice little feature. And so here, yeah, we got our sliding animations. And I like to use promises And so promises are just it's a wrapper around coroutines. And so yeah, it's just better coroutines. And it's nice for when you want to perform an action and then wait for, like on a separate thread, and then wait for the completion of it. So for example, here we have context action service. We bind this function to a key, which is E. So when we press E, that means that we want to initiate slide. And here we're saying that, okay, so as long as the promise is not started, so this is basically our way of knowing that we're not sliding, right? So if we're not sliding, then perform slide. And so do slide returns a promise. And when you have promise objects, one thing you can do is you can chain these and thens, and they're basically like callbacks, so that once the promise resolves, or once the slide is finished, we perform whatever logic is within the callback. So that's all it is. But otherwise, if so we slide when we're holding down E. So when we press down the E button, then we begin sliding, right? But then when we let go, and that's what this input state that end is for, then we cancel the slide promise. So when you cancel the slide promise, that obviously cleans up any necessary state that needs to be cleaned up wherever we were at in our sliding. It'll handle it appropriately. And so that means that the promise would be finished, would be canceled, and then we're able to, and when that promise finishes, then this callback actually gets called to say that we are out of slide. And so this should actually be like a finally, because and then only gets called, I believe, when the promise resolves successfully, right? But then when you cancel a promise, the promise doesn't resolve, it's just canceled. But if you use a finally callback, or not callback, if you use a finally callback, then it will execute this no matter what. No matter resolve, no matter if the promise resolves, no matter if the promise gets rejected or canceled. So that is what we want. And yes, so now we get to the actual do slide function. So in the do slide, we have a couple. So we have this local reset function defined. So this is for when we decide to, so it's either when we slide cancel, so like when we're in the middle of slide and then we decide to cancel, right? We let go of E. This reset function gets can be called to clean up, to do some cleanup, or if we press E, right, and then we slide. We don't cancel, but like we slide for the maximum length we could, right? Friction stops us from sliding any further, so we get really close to zero velocity, and so then this reset function will be called to handle cleanup. And and then when we clean up, and then so it'll just clean up things. So one of the things that it does is it rebinds the key. So the thing about this is that so one thing I chose to do is when you enter slide, I chose to disable the movement keys somewhere down below. And so once you get out of the slide, I need to like re-enable the movement keys. So what I do is I use user input service to check which keys is the user currently pressing, and then update some state in the controller. This is part of like the player module. And so yeah, there's some state that needs to get updated, and then update movement. So update movement will move the character based on these left right values, which are based on which keys are currently pressed. So this is just so that when we get out of sliding, we're able to just continue smoothly transition into walking. And yes, I'll get into some of this other stuff as they become relevant. So yes, this sliding function returns a promise, and you can see it's returning a promise. Here you can almost imagine this as a coroutine. And yes, there's this function reset and resolve. So when it comes time to, when this function is called, it's going to do two things. So it's going to reset the all the state, and then it's also going to resolve the promise. When we resolve the promise, that means that we're telling the promise module that, hey, we are done, this promise has resolved, we're done sliding, right? So once resolve happens, then that's how it knows to finally go ahead and execute those chain callbacks here. And yes, and then so here what I am doing is, recall there is that detect ground ray direction to detect the ground initially. And so all I do is I raycast down from the character's right leg. And if if I raycast down the character's right leg, remember it's like the center of this is knee really that we're casting down from. And then if that hits, then cool. If it didn't hit, then I'm gonna cast from the character's left leg and see if that hits the ground. And if neither ray hits, then I'm just gonna send a warning that we're not standing on valid ground, and I'm just going to resolve so that we can exit sliding. In this case, I don't call reset and resolve because there's no state to reset to begin with. None of these events have been connected. None of these variables have been set, so it doesn't matter anyway. So I just simply resolve the promise. And then here is, so this is where we are determining the vector. So this is the slope vector. So the slope vector is a vector that points along the direction of whatever slope we're sliding on. And so the way we figure that out is based on the raycast result. The raycast result, remember, we just cast it from the knee down to the ground. And so when that ray hits the ground, it'll return a raycast result. And then the raycast result has some information that is useful to us. So for one, there is the raycast result normal. So the normal vector is a vector that's perpendicular to the ground surface, right? And so let me draw this out. Right, so I'm in my trusty AutoDraw website. And so yeah, so to give an example, assume that we're looking at the side view of the slope here. Right, and then let me just make a straight slope for simplicity's sake. And then assume this blue circle is the character's head. It's the side view of the character's head. So that means that the character's, if he's looking straight down this slope, right, then his right vector would be pointing into the screen. So let's make this red vector that right vector. So it'll be pointing right there. That's like his right vector. And then, oh my God, this is gonna be hard to draw. So yeah, the right vector will be something like that. And then the normal vector of the ground surface would be pointing straight up, perpendicular to that plane, to that surface, right? So imagine, and if I can make this ground a little bit more 3D, then yeah, it'll look like more like a plane like this, right? And okay, in that case, let me redraw the characters. Right vector. Trying to erase here. Yeah. And delete. Yeah. Delete. So then, yeah, let me redraw the characters right vector. So actually, let me make it better. Make this slope better. So slope is more like, yeah, let's make the slope like this. And then I'm going to move the character up higher. Let's draw a better character. So like the character is standing on the slope, right? So then his right vector is pointing in this direction, right? But then the slope, the normal vector, which is perpendicular to the surface, this plane, would be pointing directly out of the plane, 90 degrees to the plane. So it would be like this, right? And so essentially, the direction we want to slide the character, which is pretty much the vector that is along the direction of the slope. Not quite. It's more so that this is just the direction that we want to slide the character along, right? It's the direction that the character is facing, right, along the slope. That's where we want to push the character. So then when we do the cross product, we get a vector that is perpendicular to both this green vector sticking out of the surface and then the right vector of the character, right? So now we get a vector that is along the slope, but it's essentially the direction the character is facing, but then it's along the slope. So you get a vector like this, right? And we want to apply force in that direction. Oh, and also we want to check to see if we are trying to slide up a slope, right? And it's very easy to check that. We simply look at the slope vector, and then we check to see if the y of that slope vector is positive. And if it's positive, or if I give 0.1 to give like a slight margin, but essentially if it's positive, then that means that we're trying to go up, right? And in that case, we're going to say the slope is too steep. We resolve and exit sliding. So that's why we return here. And I can show that visually as well. So basically, if we take a look at this orange vector, which is our slope vector, you can imagine that, if we're to look at the coordinates that make up that vector, that because it's pointing down, the y would be y would be negative. But if you had the character, oriented in the opposite direction, and somehow but if you had the character, let's say that the character is facing up the slope, then you'd have a slope vector. You'd end up with a slope vector that is pointing up, right? And obviously the y of that, right? Like if you just look at this triangle, right? That y is positive, right? So that means that we're trying to go up, as opposed to that orange vector where the y is negative. And if you look at the components that make up that vector, you can see that the y is, negative, pointing down. Then, so yeah, after that, we are set to initiate the slide. So we initiate the slide, we attach hitboxes. So here what we do is we fire a remote to the server to attach hitboxes, because actually you can only attach accessories on the server. And so that's why we fire a remote here. Then that remote will hit this script, the side hitbox attacher. And all we do is that we, you can see that here we add each accessory in the slide hitbox module. Remember, the slide hitbox module only has 2 accessories. It's the left footbox and the right footbox. So we are just adding those accessories to the character, which is pretty much equivalent to just like, it's basically just moving these accessories to be children of the character and then welding these accessories, these handle parts, to the character's leg. And then what we do is we created a per character accessory table where we save the accessory, the names of the accessories for, the character. And the reason why we do that is because when it comes time to remove the side hitboxes, we want to be able to reference those accessories and unparent them. What are we doing here? Card name. Oh yeah, we are just unparenting them from the character, and then putting it back in the player's backpack, essentially. And yes, that is that. Honestly, you don't need to use the name, you could just use the instance here. And then when it comes time here, you just say, accessory.parent. Right, so here we're just saving a list of accessories tied to the player's character, and then we just reparent it to the backpack when they remove. So this will no longer be accessory names, so it should be accessories. There we go, on the fly modifications. And yeah, so then when we attach the hitboxes, we fire the remote and that attached the hitbox, but we don't know, because remember, this attachment is happening on the server. On the client end, it needs to, once those hitboxes are parented to the character's model, that change needs to be replicated to the client. So we need to wait on the client for that replication to happen. So on the client end, once the equivalent happens, where I'm just using the right footbox, because they're both going to be parented at the same time. So I'm just waiting for the right footbox to be parented to the character on the client end. And once that does, we can go ahead. We can assume that the hitboxes have been attached, and we can go ahead and proceed. But also, there's this onCancel. This onCancel function is a function of this has to do with the promise module, and so this onCancel is a function. So when the promise module calls this function, it'll pass an onCancel method or onCancel function. And so pretty much what this does is we're saying that if the if the user of this promise were to cancel up to this point, use this function as a callback. And so pretty much this is for the purposes of cleanup. So that means that if they were to cancel at this point, this will be the cleanup function. And so in this case, if they cancel at this point where we haven't, where the, on the server we're attaching the hitboxes, then all we want to do is we just want to simply remove the hitboxes, because that's all we've done up to this point. You can see that later on, we are on cancel is different because in between those 2 points, if they were to cancel, then it's more complex because we're actually sliding now, right? I hope that makes sense. And so let's go further. We enable line orientation so that we can orient the character. Its velocity will be 0 to start with. And yeah, we're gonna change this humanoid state to be physics so that we can, so that the character's body will behave like a physics object, right? So that means that it'll slide down slopes and such, like a real physics object would. And here's where I disable the movement keys, character forward, backward, left, right. And so how I do that is I bind those keys using context action service to what's called a sync. A sync is simply when you bind the keys to a function that returns a sync. So this just means basically do nothing when those keys are pressed. Put the sliding animation on loop, play it. And then here we're applying a forward force. So basically here we're saying that we want to apply a force in the direction of that slope vector. And we want the force to be, mass times acceleration, right? So we get the total assembly mass of the character, and then we multiply it by the sliding acceleration. And yeah, in this direction we want to apply it along. And then so we do an apply impulse to apply a one-time instantaneous force on the character. And then from there, every frame, what we want to do is we want to do some things. So for one, what we do is we say that if floor normal, and I'll talk about where floor normal is defined in a bit, but basically if floor normal means that if floor normal is not nil, that means that we're touching ground. And so there's floor, right? And so the floor normal would be the normal of the ground surface that we are sliding along. And linear velocity is just the current velocity that the player is, the current velocity of the character. So this is a vector. And so pretty much this is pointing along the direction the character is moving. And here we're saying that, because the thing is that we want to orient the character to the surface that he's sliding on. So here we're saying that we're going to take the linear velocity, which is the current direction he's sliding, and we're going to subtract it. We're going to subtract from that the floor normal times linear velocity dotted with the floor normal. Okay, so now you might wonder, okay, what does that mean exactly? And so I'm going to draw this out. Before that, one thing I will say is the reason why I've added this is because one thing I noticed is that the physics engine, when he's sliding along a surface, it's possible for the character to sort of like bump up off of the surface. So there's there's a component of the character's velocity that is going away from the surface, imagine along the direction of that surface normal, right? So we want to remove that component of the character's velocity every frame so that he's just like sliding perfectly along the surface. There's no component of the velocity that is taking him away from the surface. I'm going to show you that in a drawing here. So basically what I'm trying to say is that it's possible that the character, slightly bumps off of the ground. So, remember the surface has a normal perpendicular. So when I say he's sliding off of, it's possible for him to bump off the ground slightly. That means that, imagine that this is the, let me use red here. Imagine that this is the player's current assembly linear velocity, right? So say it's like this, right? And it's hard to draw, but let's say that it's like this. So like there's a part of it that's obviously pointing up, right? And that part of it, and let me draw the components of that vector. So there's a part of that vector that is pointing along the slope, right? That's that yellow right here. And there's also a part of that vector that's taking him away from the slope. And that is this purple right here going up. And there is a 90-degree angle there. And so we want to take away that purple portion. And so basically what we're saying there is that we want to take the linear velocity and then we're going to project, so the linear velocity is this red vector, and then we're going to project that onto the normal, right? So when you project a vector onto another vector, you do that. That's pretty much through this operation called the dot vector, we're seeing how much how it gives you like a scalar value of how right. So yeah, if you have that this surface normal, and then you have that red vector pointing straight, or more so like this, too steep, so like this, the dot product pretty much gives you like the length of the shadow that this vector would cast on this. So that shadow would, the length of that shadow would be pretty much the length of this vector, right? So it gives you, the dot product would give you the length of the shadow, right? But then that length, you have to multiply it with the unit vector of this normal vector to get, this vector right here, like the actual shadow vector, right? So dot product will only give you the length, but to get this actual black vector, not just the length of it, we have to multiply by a unit vector of this orange normal vector. And so what we do essentially is that we're just simply subtracting that portion away. So we're just subtracting this purple. So yeah, this black vector is just this purple vector in here. So we're just subtracting that purple vector from the red vector so that we can get the yellow vector, which keeps it along the slope. So we're taking out any component of the velocity that, takes the character away from the slope. And then here we're simply using line orientation to lay the character down against the ground. So we just orient the character so that he's laying down on the ground. And in here, we are, this should just be, right, so here we're just getting the magnitude, pretty much the speed of the character, and saying that if he reaches a very slow speed, practically close to 0, then we want to, you know, recent result, you know, exit slide, because at that point, you know, he's done sliding. And remember, if he's starting out, we already set assembly linear velocity earlier here to be linear velo. So this assembly linear velocity, this speed doesn't account for any y component, like any movement off of upward of the surface, right? Going off of the surface. This is purely his lateral speed along the surface. And then here, so yeah, so this will run every frame. Every frame, once you start sliding, it'll run every frame, continuously oriented the character to whatever the current, you know, slope he's sliding along is. So this formula will continuously change, and so that's why we're doing this every frame. And every frame we're checking to see if he's finally reached a, you know, that slow speed, so that we can take him out of slide. And here we create the Raycast hitbox instance, and we pass in the character. And remember, it's going to look at, it's going to find all those damage points inside of the character's descendants. And remember, one of the descendants of the character also include those hitboxes, because they've already been attached to the character. So it's going to find those damage points, and then it's going to, we're going to pass in the ray direction. We're going to say that we want to visualize the rays, pass in those Raycast parameters. I'm going to say that on hit, so this fires if any of those rays emitted from any one of those attachments hits the ground. This is going to fire. And yeah, so then hit start here is what tells the Raycast module to start firing rays to the ground every frame. And if a ray hits the ground, then, you know, then this on hit event will get fired. And so one of the things that we want to do is we want to call hit start again, because normally when the ray hits the ground, it's not going to continue casting rays for continuous ground detection. So when you call hit start from within on hit, this is telling it to, hey, keep doing this, keep detecting ground. And so the reason why we want to keep detecting ground, because, hey, we want to keep changing the floor normal to whatever the current ground surface is. And also we want to check to see if, you know, maybe he started off on a slope that was a valid ground, like it was, you know, going downwards, so that means that he could slide on it. But maybe, like, imagine he's sliding, and then now he starts sliding up a ramp, right? There's a point where, you know, it becomes, you know, too steep, right? And then we don't want to, I mean, to be honest, anyways, if it gets to that point, then gravity and friction would probably just, you know, set him back down. But just to make the experience smooth, we don't want, we don't want him to just keep, like, sliding, you know, like a ball inside of a bowl, like just back and forth. We just want to take him out of slide as soon as he comes across a slope that is steep. So we just, you know, take him out of there. But this is a decision that you make in your, as far as it is relevant for your implementation. You can choose to change this. And yeah, so this is the initial hit start, so that we can actually start raycasting. And so one thing we do here is that you can see that there's this hit nothing promise on hit nothing event. So here we have slide hitbox stat on hit nothing. So pretty much when we're sliding and then we don't hit the ground, or none of our rays connect to a ground, on hit nothing will fire. And this will fire every frame that he's not touching the ground, right? And so here we create a promise, and then this promise. In this promise, what we do is we wait. Remember the airtime before slide stop. So this is how much time that we want to wait. So if he still hasn't touched ground within this time, we're going to reset. So we're gonna, reset, and that would exit the sliding. And you can see I did a task that spawn here. I'm going to explain in a bit why I did that. Actually, I can explain right now. So the reason why I did it is because in reset and resolve, in reset, we cancel that hit nothing promise. And the problem is that I don't want to cancel the promise when it still has, logic to execute, right? You end up with some weird error. So for example, like if this was not wrapped in the task that spawn, without this task that way, or we just put recent resolve right directly inside of the promise, then it will try to cancel the promise even though the promise is currently running. So you try to cancel the promise from within the promise, if that makes sense. And that is strange. So that's why we delay by a frame. This task that way will reset in the next frame. In the event that, we don't hit ground for, this amount of seconds. And here we just disconnect the event. Now, I don't think we actually need to disconnect the event, actually. So I'm just going to comment that out. Or no, we do need to disconnect it. But anyway, so that's the hit nothing promise. So yeah, so whenever we hit ground, we just cancel that promise, right? We cancel that promise so that, this doesn't continue to execute, right? So when we don't hit, then this time will pass, and then we would reset and can't exit slide. But if we do hit, then we end up canceling that promise, and then that cancel slide logic never gets executed because it's basically like we reset that timer whenever we hit ground again. And yeah, and then we connect the on hit nothing again to basically restart that process of like, hey, did we hit nothing? And if we hit nothing, let's start that timer to see it, if we don't touch ground for like 0.2 seconds or whatever. And yes, that's that. And then here we rebind on cancel because at this point, if the user of this function were to cancel, then that means that we're in the middle of slide. And so when we're in the middle of slide, then we cancel. We just want to do a reset where we disconnect the heartbeat event. We re-enable the controls because we disabled them. So there's a lot of things that happened, while the user is sliding. There's just so much state, and we need to reset all of that state. So that's one thing I like about the promise library is that it's robust, and you can make very resilient code that is bug free because you can cancel in the middle of at any point in this promise. You can cancel, and then you can choose how you want to handle that cancellation based on where you're at in the process of sliding. And yes, I believe that is all there is to talk about. I'm just going to go ahead and, you know, demonstrate now. So I play. And yeah, you can see he slide. And we can slide cancel. Yeah, let's see, like we cancel slide. And also notice that when we fall off, you know, you can see that the rays start following the, you know, the direction of the fall. Like gravity is influencing how we're moving. That is actually the reason why. If you look at this logic, we only remove that y component off of the surface when we're touching ground, right? Because if there's not this if floor normal check, then even when you're not even when the character is not on the ground, it will try to, it'll look like he's like sliding. it'll still look like he's sliding along that surface, that slope, right? So that is there so that so gravity can actually have an effect, right? Because otherwise we're just removing gravity, right? If we remove gravity, it'll look like we're just sliding along the slope still, even though we're in the air. I think I can actually demonstrate this. Let me stop and show you what that looks like. We don't count for floor normal. Given error 199. Okay, yeah, because we set floor normal to nil when we, if you see here, we set floor normal to when we don't hit nothing. But like if we didn't set it to nil, it might still get an error, but like I'm just trying to show you what it looks like without that check. Yeah, you see that? Or maybe you were still sliding on the ground. Okay, yeah, I don't know, but like, okay, so because I added some code here, so it's hard for me to replicate this without like, you know, triggering some weird error. But basically, yeah, that is there so that, you know, we only remove that y component when we're on the surface, because we only want to do it when we're on the surface. When we're not on the surface, if we do that, then we'll end up just like removing the effect of gravity, which we don't want. So yes, that is all. Hope you enjoyed the tutorial. I've been meaning to remake this tutorial for the longest time, and man, I'm glad I waited because I've made so many changes to the script, added, you know, features that weren't, you know, there before, and yeah, so that is all. Yeah, don't forget to subscribe, please, because that motivates me to keep making content. And yeah, maybe I'll create like a Discord channel so folks could ask questions in the Discord channel. But yeah, continue to give me ideas and give me feedback, and don't forget to subscribe. Thank you.